And then I hand it over to Chris. So the Canadian Society of Iranian Engineers and Architects, called Mohandes, is a non-profit organization which serves Iranian engineers and architects in Canada. Mohandes was founded by a group of Iranian engineers in early 1988 and has several subsections, including mechanical, industrial, and aerospace section, or MIA section. Every month, MIA section arranges a technical talk with the help from specialists and professionals from the industry for its members and public. So tonight, this month, we have Chris Barnes. And Chris Barnes is currently a strategic account manager, life sciences from Omron Industrial Automation. Prior to joining Omron, he worked for over a decade at Honeywell, developing cloud-based Internet of Things, real-time locating services, security, video, fire, HVAC, energy retrofit, metering, load shedding, lighting, building automation, and service solutions for a wide range of clients. Chris is a professional engineer with a degree in chemical engineering from the University of Toronto and an MBA from York University Sholush School of Business. Chris has been an STLE member for over 20 years and was chair of STLE Toronto in 2005-2006. So with that, Chris, please go ahead and do your presentation.
Sure. So I think you guys can see the slide here. I've got the agenda. Here's the topics we're going to cover today. It's a pretty interesting topic, and I'll just dive right into it. The reason predictive maintenance is important these days is because it's got a good payback in terms of downtime. If you can prevent unplanned downtime, you can save a lot of money, and even in healthcare lives. I've worked on some predictive maintenance projects for healthcare recently, which aren't in this presentation, but it's still interesting. Some things you can't put a price on. So lots of costs of downtime, and lots of savings if you are able to prevent the equipment from failing in the first place. Obviously, that's better than having it fail. So there's lots of studies that have found different savings. So it's pretty obvious from a financial perspective why it's important. What is amazing is how many people still run their equipment to failure despite that. So really what we're going to talk about today is what if you could prevent the downtime from happening in the first place by looking at the symptoms of your equipment and taking proactive actions in order to prevent the failure from happening. So let's talk a bit about the terminology for a minute. Predictive maintenance is also, a lot of times they call it PdM. It's basically it's also called condition-based monitoring. It's basically looking at the equipment and looking for data that will tell you that something's going wrong before it happens. It's interesting because this field developed before the technology was available to do it properly. And because of technology, if you have live real-time information, you can have a quicker reaction to a problem with the equipment and stop it from failing ahead of time. And now condition monitoring is basically getting that real-time data of how the equipment is behaving. This can be, if you're in the oil industry, this can be taking oil samples or using, sometimes people would, a good example is, I guess, your car. People used to go and check manually the air pressure on the tires with a gauge, but now the newer cars have that data in real time. So there's fewer people, if you guys have noticed, there's fewer flat tires on the road these days because their cars are telling them there's a problem before the tires go go flat. So there's a good example of predictive maintenance in action. If you are collecting live data using sensors, you can trend the data to see the patterns and abnormalities. Sometimes you'll still have a failure and you won't catch it, but you can look back at the data and see that maybe you could have caught it by looking at the data, sort of like a post-mortem, see, okay, what went wrong, and were there symptoms ahead of time. So it helps you to predict future failures, even if you don't catch them. You can also use that data to give you, especially through building automation systems or SCADA systems, to give you a live notification that something's going wrong, especially if it's in the middle of the night, and maybe you have to get somebody to go and deal with the piece of equipment, whether it's a pump or fan or whatever it is, before it causes a bigger problem. What are the key things to make sure you understand is the difference between predictive maintenance and preventive maintenance? A lot of people are used to doing preventative maintenance, which would be a good example, again, is using a car, changing the oil every, let's say, 6,000 hours or 6,000 kilometers, sorry. You're basically doing it at a certain schedule all the time. And rather than looking at the data. And then if we look at this in terms of what they call reliability-centered maintenance, which is adopted more in the military and the aviation, because you can't have planes crashing. They tend to be much more proactive in terms of looking at the data to see what's going wrong ahead of time, so they can catch things earlier, at an earlier stage in their failure curve. And here's the failure curve that's most commonly used. And basically, you're looking at the life cycle of anything from, it could be a piece of mechanical equipment like a gear or a car or anything. They're most likely to fail during the break-in period, which you have here in when the equipment's first up and running. And then obviously as it wears out and it starts to fail. We're going to talk about this curve go throughout the presentation, refer back to it, but it's a very useful tool if there's lots of information on the DIPF curve out there. We're going to talk especially today about electric motors, because for most equipment in most facilities, whether it's a manufacturing plant or a shopping mall or a hospital, it's the electric motors that are a single point of failure for a lot of pieces of equipment. If we look at the failure modes that we want to detect on an electric motor, here are different ways that can fail. And so there's a few different areas we can look at in order to catch the root cause with the failure as it's catching its early stages. These can be gather this data either from vibration analysis, current analysis, insulation resistant monitoring, thermography, ultrasonic and acoustic. And we talked about oil analysis. The oil analysis is starting to become real time. For a long time, you used to have to send the samples to the lab and get your results back a few weeks or days later. Now they're increasingly, even on cars, they're putting sensors that can detect things happening to the oil on a chemical level. The idea is you take this live data, which is really what we call the industrial Internet of Things, and use it to create, to model, to look for patterns, to predict failures, and address them periodically. And you can apply the same mentality to just about any type of piece of equipment. But for most of what we're going to talk about today, we're going to focus on electric motors, because they're very pervasive, and usually those are the most critical equipment that can't be set up in a kind of redundant manner, tend to be electric motors. So we'll look through a few different technologies in different ways. It's funny in these pictures, you have people using stethoscopes and stuff to listen for vibration, or you can measure it with a piece of equipment. So you can do stuff manually using your human senses, but you can also collect quantitative data. Other examples here, whether it's vibration, noise, temperature, you can often feel it as a human or sense it. You can hear something's going wrong. And a lot of the old school mechanics, they would know their equipment, especially if you worked in the same plant for many years, they would have a sense when something is going wrong. And you wouldn't know it if you walked in, the machine was malfunctioning. If you weren't in there every day, you might think it was a normal sound. But a lot of mechanics, they would pick up these variations. Increasingly with people retiring and changing jobs more frequently, it's harder to do it the old school. And also the technology at the same time is advanced to the point where a lot of the human senses can be done now using technology to get the same, if not in many cases, much better results, because you can there's sensors that are much more sensitive to temperature and sound than humans are. So we're going to look today at a few different of these sensors to pick up a bunch of these different failures. These are two of the ones we're going to talk about as a vibration temperature sensors combined mainly for catching up bearing failures and motor failures. And then also we're going to talk about current analysis sensors that can pick up anything from, as we were talking about earlier, as insulation resistance, leakage, and other load issues. Because if there's an issue, let's say there's a change in the load on the motor's going to have to work harder, and you'll see a difference in the current. The same way, if let's say a belt breaks and then there's no load on the motor's not going to work as hard. So you'll see that also show up in the current analysis. So it can give you that data in a couple different ways. Here's in terms of the probability of failure or different ways things fail. It gives you a good idea of the most common ones, and these are ones that are some of the easiest ones that can be addressed. You can deal with flood and stuff with water leakage detection sensors, and some of the other ones, but we're going to focus primarily on these ones here at the top. We're looking here in terms of back to the DIPF failure curve. If we go from the start and the insulation all the way to running and failure, if we look at it here, imagine this curve overlaid on here. So we're going from left to right. We're looking at over time as the motor fails, what happens and how can we pick it up. So here, if we go to insulation degradation, we can start picking that up with a sensor. If we look at the bearing failures, as the grease dries out and the bearing wear starts to happen, the vibration climbs up. We're going to be able to start picking it up with first with vibration acceleration sensors, and then with current analysis as the resistance on the motor picks up. Similarly, for other conditions, we can pick it up with the sensors. Some, such as current analysis, will pick things up earlier than vibration, whereas in bearing failure, it gets picked up by vibration first. So it's kind of nice to have a couple of different sensors that will give you clues as to what's going on, because the sensors can't tell you what's going wrong, but they'll tell you that something's going wrong. And as a human, you need to interpret the data to see what's happening. So if we look at the vibration sensors first, in terms of, they'll help you pick up those failure modes. What we're looking at as you can imagine, as the wear happens, as the machine starts to fail, the vibration is going to start getting worse and worse. And you guys probably have experienced this at home, whether it's on in your fan on your air conditioner, or your fridge or something else. It gets noisier and noisier as it starts to fail. and it reaches into the point of the wavelengths where you can start to hear it as a human, but the vibrations start out quite small. And if we can catch them with a sensor earlier, you can catch them actually before you hit a failure, which is the goal of the predictive maintenance, really catch the stuff early on. So when it's really small, we can't pick it up. You can pick this up with ultrasonic. There's some other technologies we're not going to talk about today, but there's some, you guys have probably heard of some of the ultrasonic stuff that can pick up these up early on. We're going to talk today about acceleration sensors to pick them up in this range, and then velocity sensors, which pick them up once you're below 1 kilohertz. So what's we're talking about here is a technology that combines acceleration, velocity, and temperature into a sensor that you can mount either directly on a motor. But you can also mount it onto a bearing. But this was designed specifically for motors because that's the most common failure point. It will also pick up bearings that happen along the shaft. There's some fan motors we've put it on where these motors, this sensor picks up a bearing failure that wasn't on the motor, but on a fan that was directly coupled to it. It gives you a couple of ideas. So this is, you can tap it in or you can attach it with a magnet. And again, back to where you're going to use it. We're going to also now look at the current analysis ones, what that would pick up. So you can see normal operation, a nice smooth sine wave, and then as you have issues or degradation, you see distortion in the sine wave. So that can be picked up by looking at with some current transformers picking up the data. You can see that pattern. So you put on a current transformer or CT on here. This basically shows you the load. And when it's operating healthy or normally, this is what it would look like. And as it gets distorted, it gets during abnormal operation. You can see this is not this is an unhealthy motor. And again, it's subject to human interpretation. All the data or the sensors will tell you is that there's something going wrong. And you can see it in the form here, and you can have it trigger an alarm. But what is basically telling you would have to go to look at the motor to work out specifically what's going wrong, because it could be one of these major factors, anything from problems with balancing or the coupling or insulation resistance. So it won't tell you exactly what's going wrong. It'll just tell you, hey, it's a symptom. It's almost like as a human, you can read you've got a fever. You don't know if that fever means you've got COVID-19 or something else, right? It just tells you you're sick. There's something wrong. So similarly here, this tells you there's something wrong with this machine, but the human has to look at it to determine what is exactly going wrong, and maybe you can do some analysis to see if is the shaft aligned. You can use laser alignment, or you look at different things to work out what is causing the abnormality in the data that you're seeing. And I'll show you some examples here of different things I've been able to find to detect, and they could be caused by different root causes here. There's just more explanation of what it's seeing in terms of degradation. I find it easier just to describe it where you can see visually on the pure sine wave. That's pretty easy to picture, but there's mathematical calculations that you can do. This is interesting because if you have a pump that's cavitating, so like let's say a water pump that gets air in it, this is one of the, I guess, symptoms you'll see this kind of shape on here, and almost like a doctor, you're looking at this and diagnosing. Here's what the root cause is cavitation. So when you're going to install these on a motor, you have to first pick a current transformer to match. I think there's here. So you're basically doing some calculations in terms of sizing, I'm going to skip through these because these are a little bit too on the in deep on the engineering, but just to kind of give you an idea of you're basically sizing the CT based on the current and amperage, and then once you have it installed, again, as I was saying, it can be different causes, like here with fan imbalances, insulation. Again, the data just telling you that there's something wrong when you're getting a high reading versus a low normal reading. Now we're going to switch. We've talked about vibration and current analysis. Now we're going to talk about the insulation resistance sensors. What's nice about these is you can use the same or similar current transformer to get the data. And basically, depending on how it's wired, whether it's delta or star connection, you just have to configure it a little differently. Oh yeah, that's the end of that. I'm going to switch now to thermography. Another way of getting the data is looking at the temperature. And again, this will tell you, it could be, you could have vibration and stuff at the same time, or insulation breakdown. These sensors can help catch fires such as this one before it's too late. If you have a short circuit, obviously stuff is going to be overheating, and if you can catch it before you have a big fire in your hand, that helps. The same sensors can also pick up not just the vibration, but you can pick up heat on motors. Here's some examples here for picking up things, whether it's transformers or insulation breakdown, and other wiring issues that could show up with a scan. So it's different ways of measuring temperatures in an electrical panel, whether you're doing it, with handheld. Most of these you're just checking them like a spot check once in a while, especially if you're going, you may miss it. You could have a short 5 minutes after you've been in there. So really the better way is to having continuous data, which lines up with the, we were talking about before, with the continuous live data, so that you can trend it and spot the issues earlier. And then also, if you have a failure which is unpredicted, you can go and look at the data trends and see if maybe you should have been able to catch it by looking at the data. So this is what this technology looks like. This would be installed in a panel. You could and get the data off of the live data of how if anything's overheating in the electrical panel. And then also catch things using the prediction, basically looking at the rate of rise. So the nice thing about having it monitored continuously, if you went and checked in an electrical panel and you got a reading of, let's say, let's say you got a reading of 30 degrees and the panel was ambient temperature, let's say, was 25 degrees, you might think, oh, that's no big deal. It's just running a little warm. But that 30 degrees, if you're measuring it constantly, and it sees that it's ramping up exponentially, it can trigger the alarm at 30 degrees, even if before it's gone over a threshold, just by seeing the rate of acceleration and temperature. So you can, by continuous monitoring, you can catch that short circuit or that something's going wrong. You can catch it earlier by seeing something's going wrong because the temperature is rising rapidly. Whereas if it was, like for example here, that same 30 degrees, you could have it might not be, it might be completely normal. If it's running a solid, steady line, let's say 30 degrees, that might be normal. It's more looking for the change in the pattern so that you can catch it early. And obviously, if you can get an early alarm before the stuff gets on fire, in the worst case is you're sending somebody to check that panel saying, hey, something's heating up on here, and you can catch that earlier, then especially if it gets you an alarm and and somebody wasn't at on site, if everybody was remote, and gets you into site in the middle of the night and you catch the fire before it happens, that obviously has a benefit. You can having some analytics in there that so that you don't have to program it as much, so that it automatically calculates stuff. Obviously, makes it slightly more idiot-proof if it's easier to set up. Here's some examples here. If you have a large panels, you can have multiple of these sensors here put in. Gives you an example, or you can just instead of use one or multiple. And some images here shows you what this wire here is obviously running hotter than the other ones. Here, this bottom piece is hotter, and then here you've got spots of heat in different locations. So lots of different applications here that in wide range of pieces of equipment. We've actually had people use it for even making consumer products such as candles, just to check the temperature of the product, how it's cooling. You can have this as a human interface here, or web-based on your cell phone. But one thing we've found useful is having also a local display, especially if you have, let's say, 3 pieces of equipment next to each other. It's easy to get the wrong one, so it's important when you go there. It could be any of these 3 if you just see it on your computer or your phone. Having a local display and readout turning red to show you, that's pretty important, especially in an emergency, to make sure that you shut down the right piece of equipment or troubleshoot the right one and not the wrong one. And then also having that instant feedback, if you're able to, let's say it's something as simple as a problem with a belt or an alignment problem, if you're able to fix that and it returns to normal state, to be able to see that right away locally is important. And then in terms of event history and trending, as I mentioned before, that's pretty useful. But you can also combine the sensors so that, in the same piece of equipment, if you're measuring, we see this in a lot of car plants where they have very critical production lines. They'll put not just the vibration sensors on, but they'll also put on the same motors, installation resistance and current analysis, so that for them, they really have trouble putting a price on the downtime that's just that high, that investment of 3 different sensors on one piece of equipment makes sense. And you can set thresholds for warnings and alarms, especially to try and catch stuff earlier. You don't want to set it too low, or you're going to get a lot of false alarms. And you will vibration. One of the things should point out is you'll get background noise. One of the customers we had at a hospital, they've installed these in air handling units. When the units were down, they were disturbed because they were still getting readings, and they were really puzzled by that. But then we pointed out that where they were, that's probably picking up the subway and the other vibrations you can feel in the building. I mean, you can see the background noise, which if you can feel that and hear that, it's not surprising that the sensor would pick up whatever else is going on. And in some water treatment plants in Ontario, they were also able to pick up, if they had it on a water pump, they were able to pick up other water pumps that were nearby. The peaks were lower, but you would kind of see the big peak for the pump it was on, but you'd also see some smaller ones for pumps that were especially on the same cement pad or on the same floor. In terms of data, one of the things we're seeing too is if you have that data in, if you're doing cloud computing or artificial intelligence, if you have you're trying to do the AI in the cloud, by the time the data gets from the sensor all the way to the cloud through a firewall and back again, if you're doing the analytics in the cloud, you can lose valuable time, and that latency in some cases it can mean that you're not catching a critical failure in time. So one of the things that we're seeing increasingly is putting high-powered chips at the edge and doing the AI at this level means you can get real-time monitoring quickly. And you can also have the data dump into the cloud at the same time, but sometimes it's important to have the data so you can react to it quickly. And if there's a lot of data, sometimes you don't want it going into the cloud too, because it can take up a lot of bandwidth, especially if you imagine if you take the Internet of Things to the nth degree and you put on, if you're monitoring everything, that's a ton of data that you're pushing through, and you may be missing or bogging down your network with a bunch of noise. So it's kind of have a choice. Having a choice is kind of important there, so you can decide. And here's an example of some AI controllers or technologies on the market can be used for what the easiest way to explain this is using two axes, because as a human we can see that this is an anomaly. But try and picture this if it was looking at, let's say, 20 or 30 axes or dimensions. You can't visualize that as a human. It's harder to spot these anomalies. That's really what you're getting the computer to do. Say, hey, this piece of data, something's happening with this machine that's not normal. I can't tell you what it is, but it can just tell you something's going on wrong. And so you can apply that to a wide range of different pieces of equipment, catch a bunch of different failure types. Again, it can, over time, you can train it to realize determine what the exact root cause is, but especially initially and often even after that, you need a human to work out exactly what's going wrong. But having that data to flag that there is something wrong, that's important. And we've seen examples where we pick it up so early, a human goes and checks it, so there's nothing wrong. They restart the machine, and then it fails a few hours later. It's like, well, the analytics are right, it picked it up. You just weren't able to find out what the root cause was, like what was going wrong with a piece of equipment. So it's pretty interesting field there. I'm going to go through some examples here of where where this technology helps you pick things up. Where you can have mentioned before with cavitation or airlocks and pumps. So sensor are able to pick it up in using that technology. Same thing with similar homogenizers, commonly used for milk and dairy products, as well as other things like mayonnaise, and lots of things in the food industry use homogenizers. Being able to pick up gaskets was one benefit that came out. Being able to pick that up with off of the electric motor, that's pretty interesting. You wouldn't think that would, it's not the first thing that you would think that sensor would be able to pick up. But as you find what is the root cause is that the sensors are flagging something wrong with the equipment, and you start digging, and then realizing that you're able to pick this up when you see a certain pattern. And I've got a couple examples here where it shows you the kind of the pattern here. Here we're seeing like the cavitation and water pumps. What's nice here is we've got the data in terms of what it shows, so that you're able to use that data to be able to predict them in the future, and especially when you look into the patterns. And then increases your chance of being able to correctly diagnose the root cause problem in the future. So, for example, in the homogenizers and whirring machines I was talking about earlier, it's important to catch it earlier because downtime is expensive. And on these ones, here's the I guess the configuration and where you would put the sensor. And in terms of, this is where it gets interesting in terms of the data, is being able to pick this up and what it looked like in terms of the data using current analysis sensors. So this is basically getting the electrical feedback off the electric motor. You're able to pick up a problem with a gasket on the equipment. A couple other examples here. I've got Panasonic one here. temperature monitoring, Nissan here with checking, monitoring the current on that. This one's them wanting to avoid having fires on here. This one was a thermography sensors on this one. Another one from quite a few from the automotive industry, because their downtime's so expensive. They're happy to invest in things that help to catch these things early, especially when they have. And this one, they were the maintenance, regular preventative maintenance were too late to catch them, but with predictive maintenance, they're able to catch them now. Some other places that that they're useful, whether it's picking up water pumps, whether it's in wastewater and water treatment, or in building, food and beverage, and I mentioned before, we've put them in quite a few hospitals now on critical equipment, everything from chiller plants to air handlers, cooling towers. And if you want to be really paranoid, as I was saying before with the automotive, they'll put all three of these rather than just picking one to put on a motor. They'll put a vibration and temperature, insulation resistance, and current analysis, because they all look for different. They pick up different symptoms, and sometimes one of them will pick up, depending on the failure mode, a different one will pick up the failure first. And you can also hardwire, as it's showing here, an alarm light or buzzer or visual, so you can see to flag your attention that there's something wrong. Of course, this has got a light on it too, but maybe you need if it's really critical, a siren and flashing lights, or depending on what it is. The last slide I have here is just, I think it's it's not related specifically to this, but it explains a lot of the frustrations people have. And when they're trying to make change, you really have to have a vision, the skills, incentives, resources, and action plan to successfully make change. And I think it's interesting because it shows you, what's the root cause if you have confusion? Well, it's because you didn't have a vision. If you have anxiety, it's because you didn't have the necessary skills to make it happen. If you got resistance, you haven't incentivized the employees or stakeholders to make it, for them to understand the value, or why it needs to happen. So and then if you don't have the resources, they're frustrated because not able to, either have the tools or the technology to do it. And then if you don't have a plan, you don't install it right or properly the first time. So pretty interesting. All right, that's the end of the slide deck here. I'm gonna open the floor up to questions. And
good. Thank you, Chris. So we don't have any question in the chat, but I have two questions myself. So probably other audience, maybe they have questions as well. Can you go back 2 slides? Which was almost a summary of what you said.
Just back to,
yeah, just go
this
to
one.
Yes, this one.
Okay.
2 questions. You said that they drill on the top of the bearing and they install a sensor to get the vibration and temperature, correct?
Yeah, so this, you can either tap it and drill it in, or you can use a magnet.
Sure. And
if you use the magnet, most people will put, because if it's vibrating, it will move around. Well, after they put the magnet on, most people will silicone it around it so that it doesn't move. Okay.
And so do you know what's the temperature difference that you read on the surface and the actual temperature of the bearing inside? Do you have any rule of thumb for that?
What matters most is actually, well, the temperature, because this is metal, it actually conducts pretty well. And the fins here on the motor are there to dissipate heat. So because this is connected and touching, you get a good feel for the temperature. What is important, so I gotta tell you something else I didn't mention, is there's not just a temperature sensor here, but there's also one in this unit here. And the reason that's important is because if you have changes in ambient temperature, let's say a hot day, you don't want, if you don't have a temperature here, and especially with Canada, we have the swings in ambient temperature. So in the air handling units, for example, we have this on, If it picks up a difference in the ambient temperature versus the, so what it looks at, it compares this temperature with this one and looks at the difference in between ambient and the motor temperature. So sometimes the motor temperature is rising, but the temperature in the room or it's a hot day is rising as well. And what really matters here is as the motor is starting to fail, you'll see the vibration and also the temperature. It helps having the two pieces of information together, especially with different failure modes. And the other thing, this measures has a vibration sensor as well as an accelerometer, like a velocimeter. It measures it in two ways, both acceleration and velocity. So it means you're picking up differences, and you're picking up different wavelengths. I think one of the earlier slides, I had the wavelengths for the accelerometer versus the vibration sensor. So there's actually three sensors in one here.
Sure. And as you mentioned, that was my second question. What about the displacement? So for a lower speed rotation, there should be a sensor that picks the displacement and temperature or something like that.
Yeah, let me go to these slides here, which have the numbers on it. Oh, here, these ones catch it. Yeah, so here's some of the vibration, the frequencies here.
Okay.
So the velocity sensor is going to pick it up at the lower frequency. And when it gets, really low in this range, that's when you start, you can feel the piece of equipment, right? That you get that sense of, the deep noises that you hear when something's going wrong, thuds and things, right? So,
sure. Good.
So
Thanks. Well, Fashid has the question. Fashid, you can type it. I can read it, or if you can.
Can you hear me? Can I talk?
Yes. Yes. Go ahead.
So that was a very interesting presentation. Thank you very much. Just a question I have, I'm very interested in this predictive maintenance subjects. I don't have a strong background in it. So one question that I have in terms of this, couple of sensors and techniques that you mentioned, vibration, thermography, I'm more interested in power generations. So what, is this the same sensors applies in this, in the power generation, or there would be?
Yeah, whether you're generating power, if we look at a motor, you can either turn a generator as like an electric motor in terms of you're turning this you're using as a motor, using electricity to generate rotation. But when you're using it as a generator, it's almost the exact same design. There's some differences, but you're taking this mechanical engineering and turning it into electricity. So you can apply the same sensor. It would tell you, it would again pick up if there's problems with vibration, and you pick up some interesting data off of the current as well, because you would see fluctuations in it. If you were using this in hydroelectric, for example, you would be able to pick up the difference in the water flow rates and stuff. I would think you think that would show up in the current and the output from the generator.
Yes, I mean it's in power generation, where we are talking about turbines that we are talking about megawatts. I guess the size and the RPM, I guess different sensors depends on what we are using in terms of size, thermography, materials. So that's what I was just basically getting at. But I guess the concept would be basically the same, what we are using here, what you have been
using. And so the vibration and temperature sensors, this will work regardless of the size. When you get to the current analysis on sensors, these ones, you have to size, as long as you size your current transformer. And I had a couple of slides I went through pretty quickly on that. I think I'll find them here. But they basically in here, you basically, there's different models for the the different ranges. And there's more that have come out since. We've got some that are specifically for the Canadian market. It's not showing here. We now have a whole family that's not on this that just came out this past year for the unique 575-600 volt that is in Canada and only other couple of places in the world. So it was nice that that we have those available in Canada too, because that was a kind of a gap in the Canadian market until they did that. So.
Correct. Yeah. I mean, and my second question, I'm just signed into this meeting. Do you does your company provide in-house training, or is it
well, Omron provides free technical support, depending on where. Most of these products are sold through distributors, or you can find all these products pretty much because Omron provides free technical support. They publish all this stuff on the internet very openly. There's a lot of videos on how to install these and program these. I could probably pull up a couple of examples if we have time. Get out of the presentation here. Let me pull up, and I'll just show you probably the easiest way to answer some of these questions. Let's bring this over here, and we'll just Google. I'll just put the model number in here because I know what it is. K6CM. And we'll Google that, and I'll pull up videos. And here we go. Monitoring. These are all the same technology. You could find it if you typed in Omron predictive maintenance. It would come up as well. Turn the sound off here, but you'll see. So this is them taking you through a demo of these sensors, and they'll show you how to wire them up and how to configure them. What the inputs and outputs look like. So there's lots of technical information available for free online. So wiring.
Thank you very much.
So I just Google it. I mean, a lot of companies charge for technical support, so they keep stuff quiet. The one thing that I love about my company is they publish everything. And so similar to the videos, if you wanted more technical information, if you go to all here, you'll see, try to skip the ones that are from other companies because they're usually trying to sell stuff. If you see this like Omron in the name, and you'll see, because it's available globally, you'll see in all sorts of different languages, sometimes it's Europe, Australia, doesn't really matter where, China, Japan. Omron's a Japanese company. So you'll find them in, I don't know if there's an Iranian website, but there might be. You could find them all in there. And then as you can see here, you've got images here, similar in presentation. There's a catalog here with all the data sheets. If you need those, you can download them all, specifications. And you can see in this category, which is condition monitoring devices, there's a few different technologies in here. Insulation resistance, which we talked about. We didn't really talk, we talked a little bit about this. This is that thermography, motion conditioning, but there's a few other different technologies out there, predictive maintenance sensors. So.
Thank you.
Chris, is there one that also look after the RPM and monitor the RPM of the shaft, or no?
Those are in our, we've got over 200,000 different products, so it's a bit daunting. Let me type in RPM and see. I know there's a whole bunch of servo motors. Oh, rotary encoders. There we go. That's what we want. Rotary encoders. So these ones basically will take the speed, and we use these extensively in our robotics. So if we're on a mobile robot, let me just show you what I mean by those. Let's see, mobile robot should come up here. There we go. So the reason you need these in a mobile robot is you want to know exactly where. That's strange. I'll go get at this a different way because it's not taking me in there. So the mobile robots, you need to work out its position based on how many rotations or partial rotations the tire has. Especially imagine like we do a lot of work with the self-driving vehicles to know where exactly a car or forklift or other piece of equipment is. You need to know how many, very precisely how many rotations or partial rotations you have of the wheels. Let me find it here. I'm on LD. Yeah. So if we take these mobile robots, for example, I'll just fast forward here so you can skip to mobile robots here somewhere. So if you have a mobile robot like this that are driving around delivering stuff, you know, in a warehouse or whatever, it's calculating its position partially off of the wheels. So I'll show you the bigger ones that are used in automotive plants. Oops, there, this one. So larger ones get, that's the French one. It doesn't really matter the language. Turn off the sound here. Just make this bigger. There we go. So this one will carry 1,500 kilograms. So you use that in automotive for carrying an entire body. What's happening in production is they're starting to move away from conveyor belts to robots like this, because it doesn't have to follow a conveyor line. If there's a blockage on the line, it can divert it, or if you want to skip a step or reconfigure your plant. This is like a conveyor belt that goes like anywhere. I know we're going way off topic here. It was an interesting question. I get to work on some cool stuff. So.
But these robots, they don't follow the lines on the ground.
No,
right?
they don't.
They don't.
These ones don't. They've got, this is showing you here, it's got LiDAR to make it doesn't hit anything. But what's equally important, so that it knows where it's going, is the rotary encoders we were talking about on the wheels. That's equally important for, that's how we ended up talking about this, as you were asking about, because they're very important on these, because they get their exact position and velocity, and so that when they're maneuvering, they need that feedback loop off the rotary encoder so that they know they're going exactly where they need to go. You know, when they were, you know, it helps them understand their exact position.
Okay, good, thank you.
Just one question, Nishan, can I?
Yes, go ahead.
Yeah. My first question is that these days for the motors, they are using a lot of variable frequency or VFDs. How does VFDs impact the operation and monitoring the motors, and you know how the noise or any distortion? This is one question, which if I don't mind answer that.
So if I understand that right, you're asking about using this with a VFD?
Yes.
Yeah, so it's equally important whether there's a VFD or not on this. You've got the same failure modes on there. You're just varying the speed of it. It will show on the output on this. Obviously, if you are, find a good illustration here. Right? Obviously, if you're changing the speed of the motor, you will see patterns that may show up in the vibration, but it shouldn't be abnormal. It should still be, you know, even at different speeds, it should still be a smooth ride. Like you should be able to change the speed of the motor. It shouldn't be changing the vibration on the shaft. Just the motor will be running faster or slower. Does that help to answer your question?
It doesn't impact on the, you know, situation of the motor, because when you run it fast or slower,
it would impact on the current sensors, obviously, because when you're changing usually when you're changing we have a variable frequency, a variable speed drive, you're changing the amount of power you're putting in this to making it turn faster or slower. So definitely some of that will show up in the current analysis, but in the vibration analysis, you will see some depending on the load. I'm thinking of like if you take a soft start on a chiller, which is variable speed drive on those, because you don't want to shock load it. You have it, start slowly at first. If you try to go full speed at first, and you've all heard water pumps or things that slam on when they don't have a variable speed drive, or air conditioning on a building when it doesn't have, when you don't have variable speed drive, you hear it like this bang as the air conditioning or the fan comes on. It starts with a bang, so you can tell that there's not a variable speed drive on that. This will actually, so if you have a variable speed drive, let's say on a fan, it'll come on smoother, and it's equally important to look at the vibration on there. You'll probably have longer life on that fan for sure if you have a variable speed on it, because you're not making it start as suddenly. Does that help? Or
Yeah, I got them. Another question is that when you writing FMEA for the motors, so you just the component of the motors will be analyzed for the failure, or the motors is as one component, and the other item like other mechanical items will be the other components of the failure. I want to know, is it a system failure mode analysis for FMEA, or just a component?
well, you can apply a failure mode analysis FMEA to, like, any process or part. Every time, every piece of equipment has got a different configuration, and so it's going to have different failure modes. Like if we go to whether it's an escalator or cooling tower or roof off, whatever it is, these are all going to have different failure modes. So you have to do, if you're doing a FMEA study, you have to do it on the specific piece of equipment. And obviously it's going to vary even between different brands, right?
But when you do FMEA, it is not exactly just about motor. It will be about the system, the different component of the system, like a chiller, right? Chillers has different components, so you will write FMEA for different components, not just one motor.
Yeah, so exactly. I mean, you're not solving everything. This is just the motor is just part of the solution. You're obviously going to have to, check your belts, your if it's hydraulics or gearbox, the gear oil, the chiller oil, the compressor oil, and the other components in there. There's a lot of different failure modes. This won't pick up everything, but what's interesting is the number of things we are able to pick up with it, and even some weird things like that we were able to pick up those gasket failures. That was a surprise to us. It wasn't the goal when they started using it in the homogenizers. They just were they were getting an alarm and they're trying to work out what it was, and it turned out that they were able to find the root cause on the homogenizer was that gasket failing, which is that's not what they were looking. That wasn't the goal when they put the analysis sensors on here, wasn't to find the gaskets. What they had was they were getting these alarms, and they're doing a root cause analysis, trying to find out there's something wrong on the machine, what is failing. And then when they managed to find the root cause, they found out it was the gasket. So it's when you get an alarm, you don't always know what is causing what's the failure that's causing the alarm. So
Chris, is it possible to somehow eliminate the noise from the sensor, not collecting that data and then somebody else should look at it?
I'm not understanding your question.
Well, you mentioned that, for example, you mentioned that, for example, in the hospital, there is a pump which has a peak, high noise, high peak, and then there are smaller pumps around that create some noise. So is it possible that somehow that sensor will not detect the noise and only picks the real equipment that we are looking after?
Yeah, I should pull up if I have more time, I'd go find you the graph to show it for you. Maybe what I'll do is I'll kind of, sketch one here so I can show you what. So if we imagine the data looked something, underneath the squiggle, I might go like this. Grab a free one. So the data looked like, let's say something like this for the regular pump, and then when it was picking up the pump that was on the same floor nearby, there's something like this, much smaller peak. Yeah. So they were, I mean, maybe they might have been next to each other or wherever, but what's interesting is the amplitude. The piece of equipment, that primary piece was the high peak, but they were saying, well, what are these other small peaks? And they were able to work out, oh, this is the pump that's, next to it, and this other little peak over here, well, this is a fan. They were able to work out what they were, looking at the live data, turning off other pieces of equipment. They could see which peaks disappeared. So they were able, from one sensor, they were able to see, multiple pieces of equipment. It's just kind of interesting from that perspective, right?
Yeah, but we can mask that noise, right? At the sensor by itself.
Unless you found a way to isolate the vibration, because that, I mean, sometimes they put isolation pads on chillers and stuff, but I mean, if the vibration is making it to the sensor.
Okay.
I had the same question. Like, I have used a Fourier transform infrared microscope, which measures the wavelengths
FTIR.
of the vibe. Yeah, FTIR.
I'm a chemical engineer, so I know exactly what I mean.
Yeah. So there was a time I remember I was doing FTIR analysis while I was running the sample analysis. There was a construction going on. So at the end of the day, when I was analyzing the peaks, there were a lot of like new peaks that were like, they were giving you a false signal. So, but in Fourier transform, what we do is we use various models and then we filter like the peaks that are not the right ones.
Yeah.
So is it the same thing that you apply in your algorithms, that you filter those noises?
No, so there's no filtering going on. I know exactly what you mean on the FTIR, because when I worked at Petro-Canada R&D, we used to take let's say you're dissolving an additive in an oil. If you had if you know what the oil was, and you had let's say a FTIR reading for that, and you did let's say an analysis of the finished product with the oil and the additive, you could subtract off the oil or the additive if you had those images, right? So you could see,
exactly.
We use that to look for different contaminations in the oil. But on this one, we're not doing anything on in these with the data. I mean, really what the important thing is to interpret the data. I think if you're filtering it out, you're kind of potentially missing something, because the data it's telling you there's, like in this case, the vibration. I mean, the sensors don't tell you where it's coming from. It's up to the human to interpret it. And at first when you first install the sensors, you don't really know what the data means. Like until the biggest peak is probably the piece of equipment it's attached to. That's the most obvious. But similarly with, like, if you take infrared, you can tell this is a hand here. That's somebody holding up a hand by the shape, right? But when you're first installing it on there, you're not necessarily unless you go and look, okay, what's the camera pointing at? You're not 100% sure that this is like a hand. You might say it might just be something shaped like a hand. So it's important to interpret the data when you see the different, peaks, or on the. I'm going to go back to this homogenizer one because it's interesting, because they had stuff happening here and they didn't know what was causing it, and it was only when they went and analyzed the data, then they were able to see okay, these peaks, I mean, the sensor and the software doesn't tell you, oh, there's an airlock. It's just, they seeing this peak and you had to do some, you know, root cause analysis to work out what's going on, right? And you know, they can tell when a gasket's a year old, that it's a mismatch. I mean, just this was similar what you're saying with the FTIR. By running it in different situations, they were able to see, okay, this pattern, it correlates to a brand new gasket. You know, this pattern correlates to the wrong gasket. You know, so it's kind of you know, similar with your FTIR, you have to interpret what does that that pattern mean. And here, yeah, you could perhaps using a software package, you know, take the normal and subtract this to make this make it easier to see the difference, I guess, because sometimes it's hard as a human to see the visually the difference, that there's something going on.
Yeah. Thank you very much for the explanation.
You're welcome. Great to talk about some chemical engineering for a while.
I'm a chemical engineer too, so
Oh, fantastic.
yeah.
Okay,
Great.
so any
Sir,
other
can I ask you a
questions?
question? I have
Yes,
seen
sir.
so many chemical engineers which are working in instrumentation and control, and because I am working in the instrumentation and control for more than 40 years, I'm now in OPG, and I have seen several chemical engineers are working in instrumentation and control. It was interesting for me.
Because they're not building that many chemical plants in Canada anymore. I mean, if you're in the Toronto area, there's only a handful of chemical and oil refineries you can work at, so not many.
Yeah.
Hi, Chris. I have a question. Can you hear me?
Yep.
Yes, go ahead.
Yeah. You know, the sensors you mentioned, they are like cable connected, right? They are like powered by cable, like they have to be they are not like kind of remote, right? Wireless.
Oh, these aren't wireless, no.
No. And the connection of the data is like wireless, or is like through the RGB, like port of the cable?
So this you can this doesn't show Modbus on it, but you can take it Ethernet IP or Modbus.
Okay.
You can either use, it comes with free software, or you can tie it into any of the common, you know, building automation or SCADA systems out there, whether it's, you know, Honeywell, Siemens, Johnson Controls, Allen Bradley, Omron, of course, you know, any of the different brands out there, they all talk these open protocols. So you can take the data that way. Or you can use the software will let you export it into Excel if you want. Depends if you, the idea is if you hook it in real time, you can have it hooked up on a PLC or something to safely shut down a production line or change something. If, you know, what you do with the data, how you want to react, that you know, you have to decide, okay, if there's an alarm, what's your plan of action? You know, it doesn't have to be a human checking it. It could be, you know, you could basically say, oh, we're gonna, you know, have the production line, you know, slow down or stop or whatever. It just depends on the failure modes, right, on the different pieces of equipment. So
is any like a standard protocol that they talk, you said, like between different devices, like you said?
yes, these are talking Ethernet IP and Modbus.
Modbus.
Yeah, it's not showing on here because they added Modbus. This is an old presentation. They added Modbus last year, so I don't have it on here. What's interesting though, like let's say you have these on an elevator. Pick up there's something going wrong with the elevator. You could have it, you pick it up early. You could say to the elevator, okay, you know, let the people off at the next floor, but then, then, you know, safely shut down. So you can kind of have a shutdown, a safe mode to shut down, especially you pick it up early, right?
I'm not familiar with Modbus. Like, is it like kind of like like a TCP/IP. I know how it is. Like
Yeah, so you can get, there's Modbus TCP/IP, and then there's Modbus RTU, which stands for rooftop units, which is in HVAC. Industrial, reason they came out with the Modbus, so most industrial is Ethernet IP. Like if you're using industrial controller, whether it's Omron or Allen Bradley or Siemens or one of those, then if you're using building automation, such as like Honeywell, Johnson Controls, Siemens, or any of the other ones out there, those tend to use either BACnet or Modbus.
Yeah, BACnet mostly for building management system. Most of the time it's BNet.
Perfect. Thank you very much.
Almost any BACnet system out there that you find will also talk Modbus, or worst case, you can get, there's Modbus to BACnet converters. There are lots of little protocol converters which are fairly inexpensive that you can use if you need to, change the communication protocol or get data, because it's basically the data is just, formatted in a different structure.
Perfect. Thank you very much.
Okay, any other questions for Chris?
If not, it's dinner time.
Who buys the dinner tonight?
I think my wife's already got it made, so
Good.
it's
Mr.
probably
Mahag,
eaten already.
Mr. Mahag, do you want to say some words before we close the session?
I can say I would like to appreciate from your presence, your attractive presentation, and very, very, very valuable information which you shared with us. And I'm really thank on behalf of Board of Directors of Mohandes from Chris. And I hope to see you again with some new items.
Well, you're welcome. And you can get my contact information from Bashad if you have any questions. Like I said, I've known Bashad for a decade, I guess.
More than a decade, 2006.
We have two employers, and I was at Petrochem and I went to lubrication engineers, and he was at lubrication engineers and he went to Petrochem.
So we just cross each other. Yeah. So I believe a copy of this presentation is available on the STLE website. If people wants to go and get a copy, I have the name of people who were on this presentation. I have a copy of your presentation, Chris, so I will send it to everybody directly. But if you wish, you can also get it from the STLE website. Thank you, everybody, for joining us tonight. I wish everybody a great night. Stay safe and healthy. Thank you. Thanks, Chris. Bye now.
Thank you, Chris.